this lecture we shall be talking about error detection and correction when we store or communicate some digital data. The idea is very simple. When you have some data, we store it somewhere, maybe in a hard disk or maybe some other place. With time, some bits might get changed or corrupt. Similarly, when you are sending some data over a network, over a communication channel, due to some noise in the communication channel, some of the bits again might get corrupt. So, it is a very important requirement to provide some error detection and error correction mechanism during this kind of storage and communication process. Now, there are many methods available, many sophisticated algorithms and techniques available. Now, here we shall be just giving you the basic concept and one simple method using which you can carry out error detection and correction. Okay. This is the objective of the present lecture. So, the basic concept of error detection and correction is, suppose I have a data or a number which I want to store or communicate. This is my basic data. So, one thing to understand is that whenever we are talking about error detection and correction, first thing is that we must add some extra bits to my data, because if I do, these are sometimes called check bits, let us call it CHK, check. So, if I do not add some additional bits, it will not be possible for me to tell just by looking at my data that whether the data is correct or some error has taken place. So, it is mandatory to provide some kind of additional information in the form of check bits, and the data along with the check bits will form something called code words. Okay. So, we have the concept of code words. Extra bits are added to the data and we get code words. Now, the concept behind error detection is, when we talk about code words, we say there can be valid codes, there can be invalid codes. So, code words can be valid or invalid. Normally, whenever we are storing or communicating some data, they correspond to valid code words. Now, if I design my codes in such a way, let us say I am talking about a single bit error, one bit is changing. So, if I design my code in such a way that every single bit error will convert a valid code word into an invalid code word, then my task is done. I should have a way to test whether a code word is invalid or not. So, if I see it is invalid, which means that some error has taken place. So, it was a valid code word and some bit error has converted that valid code word into an invalid code word. This is the basic concept. Okay. Fine. So, let us talk about one definition here, distance between code words. Let us say we have two code words Ci and Cj. The distance between them, sometimes it is denoted as distance Ci and Cj. It basically means how many bit positions are different between Ci and Cj. Let us take a specific example. Consider a code word 01001 and 11100. So, how many positions are different? First position is 0 and 1, it is different. Second position is same, third position is different, fourth position is same, fifth position is different. So, number of differing position is 3. We say that the distance between the code word is 3. So, the reason we are talking about distance is that the distinction between valid and invalid code words are often based on the concept of this distance. So, this is the kind of scenario I talked about, I have valid code words, I have invalid code words, and there should be a mechanism, I said, to check whether a code word is valid or invalid. Let us say our task is to detect single bit error. What I claim is that if this is my requirement, then the distance between any pair of valid code words must be at least 2. Why? Consider two valid code words, let us say C1 and C2. I am saying that any single bit error will transform it into an invalid code, right. Single bit error means what? I am increasing the distance by 1 with respect to C1 or C2. Now, if distance of C1 and C2 was less than 2, suppose C1 and C2 distance is 1, let us say, let us take an example, C1 is 1 0 0 1 0 and C2 is 1 0 0 0 0, only one bit position is changing. Let us say the distance is 1. So, it can happen that the valid code word C1, there is a single bit error on this position and it has become 1 0 0 0 0, which is also a valid code word. So, valid remains valid. Okay. So, distance of 1 will not satisfy my property, distance must be at least 2. So, that any single bit error will transform C1 into some other code which is not in this set, which is in the other set. So, across all valid code words between any pair, distance must be at least 2. This is the mandatory requirement. And generalizing this concept, if we are talking about detecting k errors, so k numbers of bit errors can be there, and k or less errors should not convert one valid code word into another valid code word. So, the distance here must be at least k plus 1. These are some basic theory behind the idea. Now, if I want to talk about not detection, also correction. Correction means, suppose an error has taken place, well, I detect the error. Not only I detect the error, I also find out the location of the error so that I can correct it. This is what is meant by error correction. Now, if I want to do error correction, what is the concept? You consider C1 and C2. Suppose I have this code C1, I have this code C2. There can be single bit errors. Due to single bit error, some bit C1 can go to some other state, C1 can go to some other state, C2 can go somewhere, C2 can go somewhere. Now, what I am saying is that if C1 and C2 are going to the same place, let us say here, then I cannot say that this is because of an error in C1 or because of an error in C2. What I am saying is that for single error correction, you must be uniquely able to tell that which is the code from where it has, there was an error and you had come to that, which means, so every such, say due to a single error you must arrive here, but if you want to go from C2 to here, at least 2 errors must be there. So, the distance between C1 and C2 must be at least 3. If we have a requirement like this satisfied, then only you can say that you can also provide error correction in addition. Okay? This is the basic concept. So, let us first talk about a very simple scheme for detecting errors. This is a very popular technique using something called parity codes. Parity is very simple. Parity is defined with respect to a given binary word. You check whether the number of ones in the word is odd or whether it is even. Well, there can be different conventions, but as a matter of convention you can say that you add a parity bit to your data, so that the total number of ones in every valid code word becomes even. Let us take an example. You consider 3-bit binary words like I show here. Let us say these are my data bits. It can be 000 up to 111. I add one additional parity bit to every word in such a way that the number of ones in every row you can check becomes even. 001, I add a 1, so that number of ones become 2. 010 again, 011 already it is 2, so I make it 0 even, 111 3 and 1 4. So, like this. So, parity bit you can define like this, it will be 0 if the number of ones in the binary code word is even, it is 1 if the number of ones is odd. You see, it is 1 if the number of ones is odd, if the number of ones is odd. So, this is how you add binary bits, this parity bits. Now, once you add the parity bits, what is the advantage you gain? You see that any odd number of errors will be detected. Why? Because now my code word will consist of not only my data, but also the parity, right, the whole thing. And we know that the number of ones is even. Now, any odd number of errors, which means single error, 3 errors, for larger number 5, 7, 9, will convert it into a code where the number of ones will become odd. So, if I have a checking mechanism where I check whether the number of ones is remaining even or not, so any odd number of errors will make the number of ones odd. So, it can be detected. So, I can use it for error detection, very simple mechanism. Not only single bit errors, but rather any odd number of bit errors, single error, 3 errors, 5, etc. Right. Now, let us come to a more complex mechanism where I also want to do error correction. The rule for error correction I mentioned for single error, that for 1 bit error correction I need a distance of 3. So, here I am generalizing that statement. If I want to correct up to k bit errors, the minimum distance between every pair of valid code words should be at least 2k plus 1. Now, Hamming code is one method where we can correct single bit errors k equal to 1, right. So, let us see actually how Hamming code works. The Hamming code that we shall be explaining here, that is for k equal to 1. The idea is, suppose I have my data bits or information bits, there are m such bits. We add a set of parity bits, not 1, but k number of parity bits. Okay, do not confuse this k with this k. We add k number of parity bits, so that we create a m plus k bit word. Now, these m plus k bit words, I shall take an example, will have a bit location. Like, what I mean is that each of this m plus k bit location, they will be having value. Suppose I have, this is my code word, these are my bits. So, I assign numbers 1, 2, 3, 4 from left to right like this. So, each of these bit positions I am assigning a number, and how many parity bits are to be added, there is a rule, you will have to follow this rule. The smallest value of k that satisfies this inequality, 2 to the power k should be greater than or equal to m plus k plus 1. So, suppose my information bits are 4 in number, m equal to 4. So, you see what smallest value of k will satisfy this. So, right hand side will be 4 plus k plus 1. If k is 2, left hand side is 4, 2 square, and right hand side is 4 plus 2 plus 1, 7. So, it does not satisfy. If k is 3, this is 8, 4 plus 3 plus 1, 8. So, it satisfies. So, the smallest value of k is 3 here. And in this bit assignment 1, 2, 3, 4, 5 that I had said, so I will be adding k number of parity bits. So, which of these will be the parity bits? They will be the positions which are powers of 2, like position 1, position 2, position 4, if possible position 8. Okay. So, the powers of 2 I will be inserting the parity bits in those positions only, and there are some well defined formula using which we can calculate the parity bits. I will illustrate. Let us take this example for this m equal to 4 as I said. So, for m equal to 4 we had said that we have to have k equal to 3, the value of k must be equal to 3, sorry, k is 3. So, we need 7 bits, 4 plus 3 b1 b2 to 7, and I said we inserted the parity bits in those positions which are powers of 2, that means bit position 1, position 2 and 4, these are powers of 2, and my 4 information bits are located in the remaining positions 3rd, 5th, 6th and 7th. So, if you look at the remaining, I am only showing decimal digits, you can also add the other numbers also. So, only 4 I am showing, only this 10 I am showing. You see 0 is, if you look at the information bits m1, m2, m3, 0, 0, 0, 0, 1 is 0, 0, 0, 1, 2 is 0, 0, 1, 0 and so on, 9 is 1, 0, 0, 1. Now, we are inserting parity bits in a suitable way. How? The rules are as follows. You look at this table. So, I write down the 3 parity bits P1, P2, P3, okay. And other than the all 0 combination, I write down all possible combinations 0, 0, 1, 1, 2, 3, 4, 5, 6 and 7. 0, 1, 0 is 2, 0, 1, 1 is 3, 1, 0 is 4. So, other than the all 0 combination, I write down all 7 combinations, and the 7 bit positions I write on top 1, 2, 3, 4, 5, 6, 7. For P1, you look at which positions are having 1 here, here, here and here. So, those are positions 1, 3, 5 and 7. So, I note them down here 1, 3, 5, 7. P2 is having here 2, 3, 6 and 7. 2, 3, 6 and 7, and P3 is having in position 4, 5, 6, 7 here. And now, I can write down the parity generation formula like this. This symbol indicates modulo 2 sum, this we introduced earlier, modulo 2 sum. See, P1 corresponds to 1, 3, 5, 7, right, 1, 3, 5, 7, out of them 1 corresponds to the bit position 1 corresponds to P1. So, remaining are 3, 5, 7. So, in 3 what we have placed M1, 5 is M2, 7 is M4. So, M1, M2, M4 modulo 2 sum of these. Talk about P2. P2 is 2, 3, 6, 7 and P2 is already in position 2. So, 3, 6, 7, 3 is M1, 6 is M3 and M4, M1, M3, M4. Similarly, 4, 5, 6, 7, 4 is your P3, 5, 6, 7. So, M2, M3, M4. So, like this you can calculate the parity, like let us take, I am taking an example, let us consider that 9, the last one. P1 is M1, M2, M4. So, you recall this parity indicates whether the number is odd or even. If it is odd, it is 1, if it is even, it is 0. This modulo 2 sum works like that, okay. That is parity. So, M1, M2, M4, you see M1, 1, 0, 1, 1, 0, 1 his even number of ones. So, it is 0. Then P2 is M1, M3, M4, 1, 0, 1, again even. So, P2 is also 0. P3 is M2, M3, M4, 0, 0, 1, it is odd, that is why P3 is 1. So, in this way you fill up all the parity bits, right. This is how you do. Now, after you have done this, now you need to detect and correct errors. See, correction of errors are fairly simple. See, in the previous slide you see that P1, P2, P3 you have calculated using these numbers 1, 3, 5, 7, 2, 3, 6, 7, 4, 5, 6, 7. You remember these numbers. You straight away find out 3 check bits C1, C2, C3 just by taking modulo sum of those corresponding bits 1, 3, 5, 7, 2, 3, 6, 7 and 4, 5, 6, 7. You see these are these numbers 1, 3, 5, 7, 2, 3, 6, 7, 4, 5, 6, 7. And this modulo sum means I am repeating, if these bits number of ones are even, then C1 will be 0, if number of ones is odd, it will be 1. Now, the rule is simple. After you have calculated these check bits, if you find that it is all 0, which means there is no error, but if it is non-zero, it means there is an error, and whatever you have got, that will directly give you the position of the error. Let us take an example. Suppose I have a code word, let us take one of the valid code words I am taking from that table, let us say 1 0 0 1 1 0 0. This was the 7-bit number. Let us say this 0, there is an error and this 0 has become 1. So, now my code word has become 1 0 0 1 1 1 0. This bit is in error. Let us try to calculate using these formulas. So, what will be the value of C1? 1 3 5 7. This is 1 3 5 7, even number, it will be 0. C2 2 3 6 7, 2 3 6 7, odd number, it will be 1. C3 4 5 6 7, 1 1 1 0, again odd number, this will be 1. So, you see C3, C2, C1 will correspond to 1 1 0. So, what does 1 1 0 mean in binary? It is 6. So, bit number 6 is in error, 1 2 3 4 5 6. It will tell you exactly which bit position is in error, and since you know that position, you can change this 1 back to 0, you can correct it. So, this you can verify with some other examples also. You will see that for any bit position error out of this 7, single bit error can be corrected in this method. This is the advantage of Hamming code, right? Using just few parity bits, you can detect and correct it. Just let us work out another one. I am just giving you the schematic, the rest I shall leave you as an exercise to verify. Suppose we extend the concept, we want to design a Hamming code for m equal to 5. So, again look at that inequality, how many parity bits we require, smallest value of k, you can check, it will be 4, because 2 to the power 5 is 32 and 5 plus 4 plus 1 is 10. But if you take it 4, 16 and okay, 4 is 6, sorry, k is 4, 2 to the power 4 is 16, 5 plus 4 plus 1 is 10, 16 greater than equal to 10. But if you take k equal to 3, then the right hand side will become larger. So, the first thing is the bit assignment. So, I said there will be 5 plus 4 9 bits B1, B2 to B9. The 4 parity bits you assign the powers of 2 1, 2, 3, 4 and 8. The rest you fill up with the information bits M1, M2, M3, M4, M5. So, 4 parity bits as usual you write down their binary equivalents other than all zeros. Then you see that how these numbers are stacking up. Let us say P1 will be correspond to 1, 3, 5, 7, 9, 1, 3, 5, 7 and 9. P2 will be 2, 3, 6, 7, 2, 3, 6, 7. P3 will be 4, 5, 6, 7 and P4 will be only there are 2 ones you can see 8 and 9. So, in this way you can actually design the check bit mechanism. You can also fill up the table, you can fill up the parity bits using these formulas just like the previous one. So, I leave it as an exercise for you to work it out and see how it works. And here also you can check that if there are any single errors, bit errors, it will be detected and also corrected, right. So, with this we come to the end of our very short discussion on error detection and correction. From the next lecture onwards we shall be moving on to the actual logic gates and their implementation. Thank you.